Добрый день
Good afternoon.
всем присутствующим на нашей конференции. Сегодня у нас по программе 4 доклада. Первый
So
из
today,
них
today we are having 4 reports all in all.
Первый доклад будет приглашенным.
The first one is for an invited presenter.
Время докладчика 25 минут плюс 5 минут на вопросы.
Now, as you know, the presenter has all in all 30 minutes, 25 for the presentation, and 5 minutes is devoted to the answer and question session.
Следующие 3 доклада будут длительностью по 15 минут и 5 минут на вопросы.
Next 3 presentations will last only 20 minutes. 15 minutes are at your disposal for presentation and 5 minutes for question and answer session relatively.
Вопросы докладчикам задаем письменно, в чате. Ну, желательно их писать по-русски, потому что у нас присутствует переводчица, как вы поняли, чтобы всем было понятно.
So, okay, students, as you know, you can post your questions in the chat. So, if you are able, you can do it in English. If you are unable, you can do it in Russian. Yes. So, and we hope that there will be a real discussion.
Ну вот, пожалуй, все с регламентом. И начинаем наш сегодняшний семинар.
That's all about our schedule today. So let's start our seminar.
Первый доклад Кристиан Темст, Бельгия, приглашенный 25 минут плюс 5 минут на вопрос.
The first presenter is from Belgium, yes. So, and it is an invited presentation. Therefore, there is 25 minutes for the presentation and 5 minutes for answering the questions, for dealing with the questions. You are welcome.
Good morning. I hope you can hear me. So, good morning, dear colleagues. Dobry den. Thank you very much to the organizers for this invited talk. I really appreciate this. I also would like to congratulate the organizers for the fantastic organization of this online conference. And so, in line with the topic of this conference, today I would like to show you some of our work where we have modified the properties of a material, mainly the magnetic properties, by doing ion implantation. And more in particular, we're going to look at the phenomenon of exchange bias in oxygen implanted cobalt thin films. Now, how do I go to the next slide? Okay. So first of all, the outline and the motivation of our work. We are interested in the phenomenon of exchange bias that is actually the coupling between a ferromagnetic material and an antiferromagnetic material. And one of the most simple but also one of the most interesting systems that shows exchange bias is by taking cobalt as the ferromagnetic material and then simply oxidizing it so that you get a thin layer of cobalt oxide, and cobalt oxide is an antiferromagnet. This is a system that has been studied for many years. However, there are very limited possibilities for tuning the exchange bias effect because you just have to work with the natural oxide that is forming on the surface of a cobalt layer. And so it has been our aim to try another approach, namely not to use natural oxidation of cobalt, but rather to create the cobalt oxide by doing implantation of oxygen ions into a cobalt layer. And in this way, we want to see if we can modify the magnetic properties of the layer. So what I will show you then today is a number of examples where we first of all show that this really works to create exchange bias. I will talk about the influence of the amount of implanted ions. And then I will also show you that we can measure the magnetic depth profile by making use of neutron reflectivity. And in the end, I hope that I have been able to show you that by modifying the properties of the magnetic layer by ion implantation, there is much more freedom to tune the effect. Okay, so first let me say a few words about exchange bias. I think that everybody is familiar with a magnetic hysteresis loop measured on a ferromagnetic material. This is this loop that you can see here. If you just take a ferromagnetic layer, then you will measure a hysteresis loop that is symmetric around zero field. But then when you look at the cartoons here at the left, there you actually look at a bilayer where at the top there is a ferromagnetic cobalt layer, and then at the bottom there is a cobalt oxide layer. And when you're at room temperature, you're above the Néel temperature of the antiferromagnet. So the antiferromagnet is disordered, and there is of course ferromagnetic order. And then you will measure just a normal hysteresis loop. But it becomes interesting when you take this system and you cool it below the Néel temperature of the antiferromagnet, because then you will also establish antiferromagnetic order in the cobalt oxide layer. Exchange bias then refers to the very strong magnetic coupling that is occurring at the interface between the ferromagnet and the antiferromagnet. And this is really an exceptionally strong coupling. The result of that is that when you apply a magnetic field to this system for trying to reverse the spin orientation of the ferromagnet, that you have to apply a much larger field than for the ferromagnet alone before you are able to break this strong magnetic coupling at the interface. And so this leads to a hysteresis loop that is much broader than that of the ferromagnet alone, and also that the hysteresis loop is shifted along the field axis. The coupling is so strong that when you start diminishing the magnetic field, it really acts as a spring, and you will even jump back to the original magnetization direction even before you have reached zero field. And so this shift of the hysteresis loop, this is what we call the exchange bias. Now, this effect has been studied for more than 50 years, but still quite a lot of things are not known about what is happening at the interface and also how the magnetic depth profile in such a layer is looking. Although this effect is currently used in many applications, think for instance in spin valves and sensors as they are used in read heads of a hard drive. Okay, so up to a couple of years ago, the simplest way of making such an exchange bias system is by simply making a cobalt film, exposing it to air, and then you get a very thin layer of cobalt oxide at the top. This is typically 2 to 3 nanometer thick, and it doesn't grow any thicker because there's a self-limiting nature of oxidation. Now, if you look at the magnetic hysteresis loop of such a system, then here in black, you see the hysteresis loop at room temperature. Nothing special about it. It's just a ferromagnetic hysteresis loop. But when you cool down to below about 150 Kelvin, then you will establish antiferromagnetic order in this cobalt oxide. And then you see this blue hysteresis loop. And you see, like in the cartoon before, that it is much broader than before. So you gain in coercivity of the layer, and that it is also shifted. You also can remark that the shape of the loop is not symmetric. It's very straight and vertical here, but it is much more rounded on this side. And this is a peculiar phenomenon in exchange bias, which indicates that the magnetic reversal mechanism is different in the two sides of the loop. And then if you measure again the hysteresis loop and again, you also see that the shape is changing once more. This is the so-called training effect. So this has been studied in a lot of detail, but as I said, the big limitation is that you cannot play with the thickness of this cobalt oxide layer. So what we have been trying to do is to take an entirely different approach. First, we have grown a thick cobalt layer with molecular beam epitaxy, and then we put a gold layer on the top so that there will be no surface oxidation of our cobalt layer. And then we have taken this sample, and then we have implanted ions of oxygen with an energy between 30 and 60 kiloelectron volt. And so what's happening then is that in the ion implantation process, you actually get a profile, more or less a Gaussian profile of implanted oxygen throughout the thickness of the film. Initially, we have used implantation conditions so that you get up to about 14% of oxygen in cobalt. We do this in our facility in Leuven, which we call the Ion and Molecular Beam Laboratory, and which consists of a number of equipment that are all integrated with each other. Here you have the ultra-high vacuum system with 2 molecular beam epitaxy systems where we can make the film, but this is also connected with 2 ion sources or separators, and in one of them we simply produce a beam of oxygen ions, and this goes in here, and so the implantation occurs here. So by the way, this laboratory is part of a European project which is called Radiate, so also external users can come to us and use this equipment. Okay, in the ion implantation process, what actually happens is that you have a separation magnet that picks out just one isotope. In this case, it's oxygen 16, and you bring that beam into the sample. So if we blow up what's happening into the sample, you see here you have the substrate, here you have this thin gold layer, and this is a simulation of the distribution of oxygen ions into the film. You can see at the maximum, which is more or less in the middle of the layer, which is 100 nanometer thick, you have about 13% of oxygen. We did this with a fluence of 10 to the 17th ions per square centimeter and an energy of 60 kiloelectron volt. Now let's take a look. We're going to compare the exchange bias on the bilayer. This is the picture that you have seen before, and we're going to compare this here with the exchange bias effect on our ion implanted system. Please note that the field scales are exactly the same, but you see that the hysteresis loop in our ion implanted system is really much broader. So this ion implantation leads to a really radical modification of the magnetic properties, and we have an exchange bias effect that is several times larger than what has been observed before. So this is an interesting result, and we have then looked more into the systematics of it. For instance, here you see the influence of the amount of oxygen ions that we implant, so that is the fluence dependence. Here on the horizontal axis, you see the fluence of oxygen ions. And what is important here is to see that on the upper part of the graph, you see that the coercivity increases when you put more oxygen into the layer. And here on the bottom part, this is the so-called exchange field. That is the amount of field or the amount of the shift of the hysteresis loop. And what you see here is that you need a minimum amount of oxygen before exchange bias appears, and that it then saturates at higher fluences. So what this actually means is that you simply have to create a minimal amount of cobalt oxide before you can start to pin the ferromagnetic layer. Okay, now the question that remains is the following. So instead of having a single interface between cobalt oxide and cobalt in the bilayer, we now have a distribution of cobalt oxide throughout the entire thickness of the cobalt layer. And then the question that arises is, what does this look like magnetically? Can we establish a magnetic depth profile, and can we say something about the way that magnetization is reversing in such a system? And so a good way to probe that is to use polarized neutron reflectivity. And I will say a few words about that. In polarized neutron reflectivity, you do essentially the same as in X-ray reflectivity. So you measure the chemical depth profile of the layer, but when you use polarized neutrons, then you can also get information about the magnetism. In particular, what you need to do is you have to use a beam of neutrons that is polarized either up or down, and you have to measure again the polarization of the neutrons after reflection from the film. And so you can have two cases. One process in which the neutron spin is conserved, that's a so-called non-spin flip process. And this provides information about the magnetization component that is parallel to the applied field. But you can also measure the amount of neutrons that reverse their spin. So this is called the spin flip process. And this will provide information about the magnetization component perpendicular to the applied field. So by doing this and doing this analysis, you can actually measure in a vectorial way the magnetization direction in your sample. And this is what I show here. So this is a reflectivity curve measured with up neutrons, these are the blue dots, and with down neutrons, these are the red dots. And the blue and the red lines are a fit to the data. So what you see here is the reflectivity plotted as a function of the scattering vector, or you could also plot that as a function of the 2 theta angle, just like in X-ray reflectivity. So what polarized neutron reflectivity does then is that you measure the chemical depth profile, like in X-ray reflectivity, but additionally, you also measure the magnetic depth profile. And the fittings that I show here are in fact simply made with a model where the magnetization is largest at the top and the bottom of the film, but smaller in the middle of the film because some of the cobalt has been transformed into cobalt oxide. And you see that we actually can get a good fit with such a model where you have a sort of distribution of the magnetization as a function of the thickness. I can show you that in more detail in this graph. This is our measured hysteresis loop, and we have then measured the magnetic depth profile along the hysteresis loop in these different field points that are indicated on the graph. And you see these different measurements here on the left. And what you see here in this column is the so-called scattering length density. So that is, in fact, you can say that is a reproduction of the magnetization depth profile in the layer. You see here that we have this sort of Gaussian distribution of the scattering length density. And this fits really very well to the data. So what we see here is that in the end, the magnetic depth profile really correlates well with the Gaussian oxygen implantation profile. So by doing the material modification with the ion beam, at the same time, you are then in fact modifying the magnetic properties. Now, you can measure the magnetic depth profile by doing a reflectivity scan, but there is more that you can do with neutrons. You can also gain information about the magnetization reversal mechanism, meaning that you can see if there is domain wall nucleation and motion, or if there is a coherent rotation of the magnetization. And this you do by making so-called field scans. So that means that you stick to a fixed scattering angle and you measure this up and down neutron reflectivity as a function of the applied field. And here I draw your attention mainly to these graphs at the bottom in red and green, because they are the so-called spin flip intensities. Remember, this is providing information about the component of magnetization perpendicular to the applied field. If you have a process of reversal by only domain wall nucleation and motion, there is hardly any component perpendicular to the field, like here. But when there is a process of rotation of the magnetization, you see a peak in this spin flip. The upper part here was well known. This is for the bilayer, where you have a switch in the magnetization reversal mechanism from domain wall nucleation to rotation. In our implanted system, we see that it is always domain wall nucleation and motion. So we have modified the system in such a way that the rotation of magnetization is no longer occurring. Now, finally, and I move to the end of the talk, we have done one more thing. So with our initial implantations, we have a Gaussian-like distribution of oxygen into the layer. In a next step, we have then done implantations at different energies so that you get to a more uniform profile of oxygen throughout the entire layer. And then we have compared that to what we had before. And so, again, we have done a more detailed study of the magnetic properties as a function of the fluence. So first of, because we had noticed that this asymmetry of reversal is changing abruptly when you reach a certain minimum fluence. So here first in the low fluence regime, you can see that there is again this shift in magnetic reversal mechanism from domain wall nucleation and motion to rotation. So this is in fact the same as what is occurring in the bilayers. But then when we look now to the high fluence regime, again I draw your attention to these curves here, which are the spin flip signals. You see that they are absolutely flat. So that means that there is absolutely no rotation of magnetization occurring. And the reason for that is that in the high fluence regime, you really are creating a very thick and well-formed cobalt oxide, which is stoichiometrically correct, which has a well-defined and very, very strong uniaxial magnetic anisotropy. And this is a regime that you cannot reach by simple oxidation of a magnetic layer. So here I would say that the process of ion implantation creates a modification of the magnetic properties in a way that you cannot reach by natural oxidation. So, in conclusion, what I hope that I've been able to convey to you is that by using implantation of oxygen into the cobalt thin films, that this is an alternative approach to generate this exchange bias, even for very thick layers, which is not so easy with surface oxidation. And we've also shown that the materials modification is really mimicked by the magnetic properties. The Gaussian profile of oxygen ions is simply also determining a magnetic depth profile that is also Gaussian. We have seen and studied in detail the fluence dependence. I've seen that there is a minimal fluence before you see the effect. And I hope that I've also been able to show that polarized neutron reflectivity, which is in principle a complex technique because you need to go to a reactor source, but that it is also very powerful to really reveal the magnetic depth profile. So the main conclusion is that the ion implantation provides really new opportunities to tune these magnetic effects. I thank you for your attention. Spasiba. And I would like to end by thanking all the collaborators who have worked on this project, And I also thank the European Magnetometry Network. Thank you very much for your attention.
Спасибо за хороший доклад.
Thank you very much for your very successful and comprehensive report.
Thank you.
Так, вопросы, пожалуйста, задаем в чате письменно.
Are there any questions? Do it in a written form. Please, we are waiting for your questions.
Ну, в настоящий момент, так, вопросов пока нет. Еще раз благодарим докладчика за великолепный доклад.
So thank you very much. There are no questions yet. So, but we thank you for your very successful report.
Thank you very much, and thank you for the invited talk. It was really a pleasure.
Спасибо, до свидания.
До свидания.
Следующий доклад делает Иван Николаев. Это Новосибирск. Вау.
Okay. Greetings, colleagues. I'm Nikolaev Ivan, and I'm junior researcher in the Department of Applied Physics of Novosibirsk State University. And topic of my report: potassium titanium phosphate sputtering features by argon cluster ions. Cluster is a group of atoms bonded by weak van der Waals forces. The cluster size can be from hundreds to thousands of atoms. And it's known that interactions of monomer ionize with surface atoms is based on individual collisions or cascade of binary collisions. But in the case of cluster ion beams, the large number of cluster atoms practically simultaneously collide with approximately same number of atoms in solid. This leads to complex nonlinear effects, in particular to local high density of energy deposition in subsurface layer less than 20 nanometers deep. In addition, collectivity interactions leads to displacement and sputtering, displacement in solid and sputtering of target atoms predominantly along the surface. By changing the cluster size, it is possible to form intense flux of particles with very low energy per atom in cluster, few electron volts, which comparable with the binding energy of atoms in target atoms, and with energy few electron volts is unattainable in monomer ion beams. For optical materials, cluster ion beams are potentially unique tool for obtaining ideal optical surface that is atomically smooth with sub-nanometers surface roughness and minimal damage layer, few nanometers. Here you see a general scheme of formation of accelerated gas cluster ion beam and main types and problems of formation and processing. Neutral clusters are forming during adiabatic gas expansion through supersonic nozzle into vacuum chamber. Cluster beam extract from near axis region of supersonic jet by use conical diaphragm schema. To increase kinetic energy, cluster energy, the neutral clusters are ionized by electron impact. The resulting cluster ions are accelerating focused by an electrostatic system and then directed to target. Monomer and oligomer ions are separated here from cluster ion beams by magnetic separator. For material processing, one of significantly problem is formation of cluster ion beams with the required parameters: mean cluster size, energy per atom in cluster, and etc. Okay. On this slide, general view of experimental setup, CLEOS is shown, and the main experimental parameters. The setup consists of 4 vacuum chamber, this chamber, and with differential high performance pumping system, and the system of ionization of cluster beam and system of movable sample holder. To obtain of cluster ion beams parameters, we used original time of flight technique. Without going into technical details, main difference in our scheme from unknown techniques is that the ion beams are modulated at the stage of its formation here. This makes it possible to perform measurements without any additional electrodes on limited flight path. And main advantages of our time of flight system is possibility to measure cluster sizes with any energy. Mean cluster size for different stagnation pressure we obtained from mass spectra presented on this slide. We processed samples at ionization current of 90 milliamperes because an increase in ionization current over 100 milliamperes leads to significant shift in mass distribution function to small cluster sizes. They indicate either multiple ionization or cluster fragmentation, which is undesirable. Modern technical makes it possible to obtain 2 sub-nanometer roughness for some materials. However, the properties of finished optical elements, such as laser-induced damage threshold, surface life, significantly depend on subsurface damage layer, which inevitably forms during technological material processing. For example, for fused silica, the threshold for bulk laser damage reaches 47 gigawatts per square centimeters, which is close to theoretical limits, but threshold of surface damage is almost by 10 times lower due to subsurface damage layer. Cluster ion beams ensures minimal damage to processed material, and the results of our colleagues show that thickness of damaged layer after treatment with cluster ions is several nanometers. Okay. Apart from the layer, it is important to consider surface topography. More detailed information about surface topography is given by power spectral density function of roughness. It's a function describing the distribution of irregularity heights on sample surface, depending on spatial frequency. Also, PSD function also to estimate to light scattering on optical surface and calculate effective roughness of sample. On this slide, you can see main parameters of treatment mode. Firstly, treatment modes are not high energy to cause less subsurface damage during processing. Secondly, the first mode had a high etching rate to more efficiently etching subsurface damage layer. And the second mode had low etching rate, but more efficiently. The most important universal parameter of material processing is sputtering yield, which in general case is determined by the ratio of the number sputtering targets to total number cluster ions during exposition. Recently, it was shown that sputtering yields can be described as universe non-linear depends of sputtering yields per atom on energy per atom in cluster. Non-linear depends is typical for various materials, including potassium, titanyl phosphate. The sputtering yields which are plotted in this figure. And here you see different sputtering yields of different materials, and see non-linear depends all of it. Okay, here you can see atomic force microscopy images before and after cluster ions treatment, and large scale 100 by 100 micrometers we see a slight change in roughness after processing, but also two-dimensional images and surface profiles show smoothing of traces of mechanochemical polishing, but it significantly degrades of traces primarily mechanochemical polishing, with especially noticeable on 40 by 40 micrometers. You see traces of preliminary mechanochemical polishing, and after after treatment, we smoothing surface. And at the small scales, 2 by 2 micrometers, we see greatest decrease in roughness by 3 times. And here we see that high energy mode remove scratches and traces of mechanochemical polishing, but it significantly degrades the surface profile and increases in roughness. But after second mode, heights of surface profile significantly decreased. Okay. In this slide shows spectral function of roughness. The integral of this function is effective surface topography. And we saw degradation of surface profile after first mode, and we see increase spectral function in this range of special frequencies. But after second treatment mode, argon cluster ions, which have diameter of only few nanometers, efficiently smooth irregularity with lateral size of 5 micrometers and less, which corresponded of special frequency 0.2 and higher, with a range of special frequency, which is especially important for optical materials. And in conclusion, at the small scales, we see the greatest decrease in roughness is by a factor of 3. By I don't know, but etching depth was only 40 nanometers. And it has been found the cluster ion beams can be provide effective surface smoothing with lateral irregularity of 5 micrometers or less. Since using the PSD functions, it is possible to estimate the light scattering at optical surface. And we determine this sputtering yields and etching rates for KTP single crystals. And we see low damage surface processing leads to an improvement in optical surface quality by minimization of subsurface damage layer, which is undoubtedly one is important limited peculiarities for nonlinear optical materials such as potassium titanyl phosphate. And we have proven the gas cluster ion beams can be used the superfinish processing of optical materials with initial ultra-smooth roughness. Thank you for your attention.
Okay,
Спасибо за хороший доклад. И вопросы появились. Вопрос первый. Так, сейчас я его прочитаю. Скажите, если использовать для травления поверхности кластеры, состоящие из большого количества атомов, то в чем преимущество использования более тяжелых частиц? Ведь в случае использования тяжелых и объемных частиц шероховатость поверхности будет выше, чем в случае более легких и менее объемных частиц.
Okay, I need to translate. Wait a little, please, before answering. So, will you be so kind to tell me if you use clusters? consisting of a large number of atoms for surface etching. What is their advantage of using the severer particles? Indeed, in the case of using severer or heavy and bulky or particles, the surface roughness will be higher than in the case of lighter and less bulky particles.
Хорошо. Раз вопрос на русском, я отвечу на русском.
So I can answer in Russian.
Так, преимущество как раз кластеров большего размера в том, что они имеют больше скорость травления. И
Okay,
могут...
just a minute, please. The advantage of clusters of bigger size is that they have the advantage of, once again, of what? The clusters of atoms for surface etching.
Так как скорость распыления больших кластеров больше, мы более эффективно удаляем поврежденный слой.
Okay, as the speed of spray speed is higher, yes.
Используем эффектом траем.
Скорость распыления больше, and
Поэтому более эффективно распыляем поврежденный слой.
The sputtering, so in this case we sputter more effectively their damaged layer.
Повреждения после больших кластеров все же меньше, чем повреждения после технологической обработки.
Okay, so the damage after using bulky clusters, yes, bigger clusters, are less than меньше, чем
Технологической обработки.
Than after technological processing.
Спасибо за ответ. Так, еще вопрос поступил. Кристиан Темст. Зачитайте, пожалуйста.
Okay, so very interesting thing. And can you also produce size-selected cluster beams in your equipment? Do you understand the question in English?
Yes, we use magnetic separators for size-selected cluster beams, and if we want more size-selected distribution and more size-selected cluster size, need use magnetic separators with bigger magnetic field.
Все у вас, да?
So,
Так, и у меня вопрос возник. Вот скажите, пожалуйста, что играет большую роль? Масса кластера или зарядность кластера? Вот при распылении поверхностного слоя. Как с вашей точки зрения?
Okay, so just a minute, please. And what mass of the clusters or the charge of the clusters plays the biggest role?
Большую роль играет именно соотношение энергии к размеру.
The ratio of energy to size plays the most role.
Спасибо.
Thank you.
Так, ну вопросов больше нет, я не вижу. Благодарим докладчика за хороший доклад. Спасибо. До свидания.
Thank you to the reporter.
Thank you. I also invite.
Так, следующий доклад делает Петрикова Елизавета, Институт сильноточной электроники, город Томск.
So next, do you hear me? Next, so reporter is invited. The presenter is from Institute of High Electronics. You're welcome.
Do you hear me?
Yeah, we do.
Okay. Dear ladies and gentlemen, good morning or good afternoon. It depends on where you are. And my name is Petrikova Elizaveta. I'm from High Current Electronics Institute. And first of all, I'd like to thank all those people who made this event possible. And I'd like to thank local organizing committee for the hosting this event and for the opportunity to present my work here. And the name of my presentation is formation of high-strength near-surface layers in hypertectic silicon with an electron beam treatment. I'd like to start with some background. Due to economic and environmental requirements, it's becoming increasingly important to reduce vehicle weight. For such an objective, aluminum silicon cast alloys have been widely employed to produce automotive components. And aluminum alloys with silicon as the major alloying element form a class of material providing the most significant part of all custom manufactured materials due to an excellent combination of castability and mechanical properties, as well as good corrosion resistance and wear resistivity. The microstructure of these casting alloys contains dendrites of alpha solid solution, primary silicon, crystals, and many intermetallic phases. The size, morphology, and distribution of microstructural features govern the mechanical properties of these alloys. And it's well known that a refined microstructure results in improved tensile properties. The refinement of microstructure can be achieved through high cooling rate or chemical modification. And chemical modification. And for example, we can use strontium to improve mechanical properties of eutectic silicon, and we can use phosphorus for hypereutectic silicon. And this treatment may modify the coarse plate-like morphology of silicon particles to fine fibrous. And there are no elements known that beneficially modify both the eutectic and hypereutectic phases. But also modification can lose its positive effect by addition of large amounts of modifier, which called over-modification, and which often causes the formation of brittle compounds which degrade alloy performance. And also, at the same time, the cooling rate has a marked effect on the size, morphology, and distribution of all microstructural constituents. So at our work, we use electron beam treatment, and electron beam treatment in optimum modes allows one to form a nanostructured surface layer in silicon and to greatly improve its physicochemical and strength properties, which is unattainable by conventional surface treatment. Okay. The specimens were subjected to pulsed electron beam treatment in the argon environment at a residual pressure of 0.02 Pascal, electron energy of 18 keV, electron beam energy density changes from 10 to 40 joule per square centimeter, and pulse repetition frequency was 0.3 1 per second, and pulse duration was 150 and 200 microseconds. Here you can see the appearance of electron beam in the chamber. And before treatment, we have rough surface with a big amounts of different inclusions and micro roughness. on the surface, but after our electron beam treatment, we have melting and recrystallization surface layer. So we have modified layer, which is smooth and with enhanced mechanical properties. So, the structure of the initial specimens consists of grains of aluminum-based solid solution containing silicon and other alloying elements, grains of lamellar aluminum-silicon eutectic, and precipitates of intermetallic compounds and silicon. The size of silicon varies from several to several tens micrometers. You can see silicon is here, and intermetallic compounds is here. The radiation of silicon by pulsed electron beam with an energy density of 10 joule per square centimeter leads to a slight melting of the surface, as a result of which no dissolution of silicon crystallites and intermetallic compounds is observed, and a large number of micropores and microcracks are still recorded. The treatment of silicon with an electron beam with an energy density of 25 joule per square centimeter and higher is accompanied by melting and subsequent high-speed crystallization of the surface layer. A dispersed structure is formed. You can see it here. Micropores and microcracks are melted, so we see the smooth surface with cellular structure. When irradiation in the modes used, the silicon undergoes surface melting, dissolution of silicon particles and intermetallic compounds, mixing of elements in the melt via convection, and high-rate solidification with the formation of sub-micro nanocrystalline multi-phase structure composed of dendrite cells. So we can see multi-layer structure. At this layer, we see that silicon and intermetallic compounds are melted, and the next layer we see that aluminum and silicon are melted, but intermetallic compounds are present in this layer. And so, using the method of transmission electron microscopy, it was found that a structure of high-speed cellular crystallization is formed, and firstly, there are grains in volume of which a structure of high-speed cellular crystallization is formed. You can see here. And second, there are grains in the volume of which, along with the structure of high-speed crystallization, we see the crystallites of excess globular silicon are present. It is shown that the structure formed in silicon samples during irradiation with an intense pulsed electron beam depends on the distance from the irradiation surface. And in the layer located at the depth more than 40 micrometers for 25 joule per square centimeter and 60 micrometers for 40 joule per square centimeter, a structure is observed that forms as a result of partial melting of silicons, aluminum melts, and silicon, but needle-shaped iron-based intermetallic inclusions are remain, and you can see it here. It was found that the treatment of silicon is accompanied by the formation of material, the hardness of which gradually decreases with distance from the sample surface. Analyzing the result presented here, it can be noted that the maximum value of the silicon hardness reaches in an extended layer located at a depth of from 10 to 40 micrometers when the silicon is irradiated with a beam in the mode of 25 joule per square centimeter, 200 microseconds, and 3 pulses. Mechanical and topological tests were performed it is shown that in the best case, the microhardness of the surface layer, 45 micrometers thick, increases in 1.4 times relative to the initial state, where resistance increased by near 8 times, and friction coefficient decreased by near 2 times. So, some conclusions. The analysis of strength and topological properties of the Silurian surface layer treated with a high-intensity electron beam has been carried out, and it is shown that at an irradiation mode of 25 joule per square centimeters, the wear rate decreases by 8 times relative to the original. The microhardness of the surface layer with a thickness of 40 micrometer increase in average 1.4 times in relation in the volume, and the friction coefficient is reduced by near 2 times. And as a result of performed studies, it was established that regardless of the energy density of the electron beam, 2 types of regions or grains are formed in the surface layer of Silurian, differing in the silicon concentration and the type of substructure. Namely, grains in the volume of that the structure of high-speed cellular crystallization is formed, and grains in the volume of that along with the high-speed cellular crystallization structure, globular shape exists silicon crystallites out of them. And also, it was found that the average size of crystallization cells enhance with an increase in the energy density of the electron beam in the range of 25 to 40 joule per square centimeter, from 290 nanometers to 500 nanometers. And at the same time, the transverse dimensions of the second phase interlace also increase from 80 to 110 nanometers. And that's all. Thank you for your attention.
Спасибо за хороший доклад.
Thank you very much for your informative presentation and report.
Так, появился один вопрос. Прочитайте, пожалуйста.
What is the weakness of a heat-affected zone in case of your irradiation?
We have, after our irradiation, we have modified layer. It's about 18 micrometers. You can see it here. The melted layer and the heat affected zone.
Mm-hmm.
And the next questions I can.
Why do you use 5 pulses for irradiation and not 1 pulse for irradiation? Can't you get such results by using of 1 impulse? Why do you use impulse duration of 150 and 250 milliseconds for irradiation and not 100 or 250?
We use not 5 but 3 pulses for irradiation because of I don't know how in English say пробой. Иногда встречаются пробои на.
There are sometimes breakdowns. Yes, so.
Yes, so we don't use 1 pulses to get a stable result.
So next question is, what is the fraction of material evaporation?
No, it's about microsecond questions. This second part of question from Vladimir Denisov, that we use 150 and 200 microseconds for irradiation because some calculations were conducted and we revealed that we use this regime to get structure what we need.
Okay, thank you very much. Olga Krisina has the next question. Is it possible to enhance the properties of Silurian that you have got?
Улучшить свойства. Yes, we we can align. For example, we can напылять. We can align our material with our electron beam. At first, we use, for example, titanium or zirconium, and we deposited it on our surface, and then we melt it with our electron beam. So we can get more. We can get better properties than we have.
Okay, Alexander Ligachev, yes, a strange question. Who from industrial practitioners needs such kind of high qualities?
So we can I say in Russian? I don't know. Силумины можно использовать в парах трения, and we start this project with our Belarusian colleagues, and they use it in в парах трения, в общем.
Where?
Пары трения.
Thermocouples for friction.
Okay, for friction, yes.
Так, все, вопросы закрылись. Спасибо за хороший доклад и очень хорошие ответы.
Thank you very much for your detailed report and for very good answers.
Thank you, bye.
До свидания.
Bye.
В описании у нас еще один доклад. Докладчик из Улан-Удэ, Мишек-Дорджин.
We have one more reporter from Ulan-Ude, Undrach Mishek-Dorjin. Sorry if I am mistaken in the pronunciation of your name or surname.
Hello?
Hello.
Can you hear me?
Yeah.
Okay, because of low quality connection, let me turn off camera. So, okay, so let me start. Dear conference organizers and participants, let me present today the report entitled Electron Beam Surface Modification of Low Carbon Steel. Okay. So can you turn to the next page? Okay. Sorry. So we shall discuss today thermochemical treatment, its advantages and limitations, then electron beam surface modification, then objective and materials, experimental procedure, then results of metallographic, microhardness, and XRD. After that we come to conclusion. Abbreviations which will be used today are electron beam alloying, EBA, thermal chemical treatment, TCT, and electron beam processing, EBP. Before we start, let me say about motivation of our research. Thermochemical treatment, or TCT, is a common method of surface engineering. The most known processes are boriding, which is on the right picture, and boroaluminism is less known. So it is a process where boron and aluminium both diffuses to the surface of steels and alloys, and form boron aluminides and iron borides, iron aluminides, which allow to increase wear resistance and oxidation resistance at high temperatures. So the advantages of these two processes are high hardness, up to 2300 HV, then low friction coefficient, high wear, erosion, corrosion, and oxidation resistance. And disadvantages are high surface roughness, as you can see on both pictures, and inhomogeneity of the layer. If you will take a look on the left picture, you can see that complex microstructure divided into several sublayers. So, and each sublayer has own phase composition and morphology. So this is kind of negative properties, and so one of the also huge disadvantages is high brittleness of ferrum boron phase, which is on top of the layer. So these limitations encouraged us to provide research in electron beam surface modification. We did this in two ways: electron beam alloying, and where treatment paste were pre-applied to the surface of steels, and then electron beam was heated the surface to create coatings. And the second way is combined treatment on the right, where we provide a first thermochemical treatment as a first step, and then EBP process as the second step. So you can see that diffusion layer, previously obtained diffusion layer, can be heated by electron beam, and result in morphology change, and so huge transformation of previous obtained diffusion layer, which result in properties, changes in properties, and of course microstructure. So based on that, our objective of the study is to obtain coatings and layers with high mechanical and thermal physical properties on the surface of low carbon steel. Steel ST3 was used as a tested material. It is used for load-bearing elements of structures and parts operating in positive temperatures. So before experiments, samples were cut into rectangular pieces, and for treatment paste we used powders of aluminium and boron carbide. In addition, sodium fluoride as an activator, where aluminium and boron carbide ratio was taken as 1/5. So electron beam processing was done on installation, which is presented on the left. Treatment parameters are discussed on the right side, so where you can see specific density, residual pressure in vacuum chamber. And let me point your attention to the table below, where you can see the mass change before and after EB. For example, initial mass with treatment paste was 14.6111. After EBA process, the mass reduced to 14.5060. So the sample lost approximately 0.1 gram. And duration of the process was 55 seconds, and for the second process, approximately half of a minute. Next. And pharmacochemical treatment as a first step of combined treatment was done in the following order. So where treatment paste and sample were placed in cylindrical molds. After drying, molds were removed and obtained briquettes were dried for about an hour. After that, they were placed in preheated to a treatment temperature of 950 degrees Celsius in muffle furnace for 2 hours. After treatment, samples were cooled down at ambient temperature, and after that, samples were subjected for further preparation procedures such as cross. As a result of treatment, so wait a minute, yes. As a result of treatment, we obtained coatings of around 250 micrometers. You can see that dark dendrites are visible, which are placed in light matrix. Also, base metal ferritoperlite microstructure is visible, and also perlite rich zone in transition zone just below coating. Also, you can see, and microhardness distribution showed that the maximum microhardness is 14-15 HV on the top of the layer, and then values decreases, slowly decreases to value of around 200 HV in base metal armature. And the phase composition of obtained coating is ferrum 2 boron, iron boride, then iron carbide, then iron aluminide, and sodium fluoride. So these 4 phases were established during XRD analysis. And as a result of thermochemical treatment, so layers of around 130 micrometers thick, what you can see the thick middle zone, light zone, is usually ferrum aluminides, and iron borides concentrate on the top of the layer and in between the layer and substrate in the form of dark crystals. And subsequent electron beam processing of this diffusion layer resulted in huge transformation of the layer. After that, we obtained light dendrites in the structure, so the thickness of the layer increased by 2 times, and also you can see that base metal microstructure changed. So the crystals or grains of the base metal, so the EBP process resulted in coarsening of base metal grains. So this is results of combined treatment microstructure, and microhardness distribution showed us that maximum microhardness after TCT is around 700 HV. On the graph, it is marked as in the. After that, values drastically drop to around 200. On the contrary, microhardness distribution of combined treatment, which is like HTO plus LO, so we can see vibrations in the values. Vibrations from 550 to 350 HV, and then values drop and gradually drop to around 200 HV. So by this time, we haven't done yet with EDS and XRD analysis for still ester-free, but I can show the results which we obtained on 21, which is analog to FreeHAT 2V8F still. take a look on the aluminum distribution after TCT, you can see that the maximum values, the maximum concentration is on the top of the layer, then values gradually decreases in the direction to the concentration decreases in the direction to the base metal. And after EBP process, aluminum distribution is more even. And XRD analysis. 1 minute, so it is quite slow. Yes. XRD analysis on tool steel H21 have shown that initial phase composition drastically changed after EBP process. So all phases actually changed. So by now, let me make these conclusions. So it's a bit slow. So I conducted experiments on combined treatment, generated the following findings. Combined treatment resulted in predominantly aluminized layer formation with a thickness of around 130 micrometers and simple microstructure. The subsequent EBP modification of the layer leads to transformation of its microstructure and enhancement of the layer thickness up to 400 micrometers. In addition, metallographic analysis showed that the combined treatment results in coarsening of grain size in the base metal just below the layer. The microstructure of the layer after both combined treatment and EBA process is similar. However, the first treatment results in formation of light dendrites in the layer, and the latter process dark ones, which indicate phase composition difference. It should be also noted that EBA process has the lowest impact on the base metal microstructure and provide higher micro hardness in the layer. The conducted research was supported by Russian Science Foundation grant. Authors are grateful to the staff of institute and university. So thank you very much for your kind attention. Report is finished.
Okay, we have a question from Maxim Vorobyov. Slide 11. Dion Rach, how can you explain the local minimum on the curve, the radiation curve?
Okay.
Slide 11.
Slide 11.
Slide 11.
I think so. Oh, okay. After radiation, local minimum. Yeah, it's a good question. I think this minimum relates to the phase composition difference. So this is the one theory, and the second theory, we think also it is related to the electron beam influence, which affect like pulse values and results in some soft depending on its depending on its frequency. So we obtain soft and hard phases depending on the thickness of the layer. So, but I think this minimum of around 400 HV local minimum probably relates to the phase composition. So on this distance from the surface of around 50 micrometers, probably soft phases are so majority of the soft phases concentrate on this thickness.
Okay, thank you. Next question is from Alexey Markov. What about roughness and cracking at the surface after EB treatment?
Okay. Yeah, it's a very good question. Surface of roughness, if on the first part of presentation, so it was reported that roughness of the surface after thermochemical treatment is quite high, and one of the objectives of our research was to reduce it by electron beam processing. By now we haven't measured it by numerical analysis, but and I can't give you by this time any numerical results. It's there is only visual comparison between before and after EBP process, and it looks like after EBP, so the surface roughness is also quite high. But one of the possibilities to reduce the surface roughness is to provide post-mechanical treatment like thin grinding or polishing. So if we will find any application, but it's very much depend on application. If any part or any detail need a high quality surface roughness, of course, it is not possible to obtain directly after EBP process. We need to provide additional mechanical treatment like thin polishing.
Okay, thank you. Next question is from Nikolai Kuksanov. What will happen if you increase the beam energy?
What will, yeah, it's also a very good question. We would like to know. We haven't done yet with beam parameters. We only changed duration of a process, and it is very interesting to see what will happen after increasing beam. So beam energy, and I think the temperature, first of all, temperature will rise, and in some cases it is not so positive because the surface will too much how to say, I forgot word, will
melt.
Yeah, will melt. Yeah, it will melt more quickly. So we need to shorten to reduce the treatment time. But there probably, or there should be another processes which very interesting to see. But so by this time we haven't done experiments with increasement of beam energy. But for sure we will do that in the future.
Okay, thank you. Next question is from Olga Krysina. It is in Russian. You may see it, but I should translate it into English for our English-speaking colleagues. So you have a very large layer thickness with a homogeneous elemental composition after electron beam treatment. Will you be so kind to tell us more about the parameters of the electron beam?
Okay, so the parameters of electron beam was presented at the beginning of the presentation, and yeah, so these are the parameters of electron beam. Yeah, it is definitely that we obtain quite thick layer, and so in some cases it is desirable, in some cases it's not. So it's very much depend on the it very much depend on what is demanded by a particular detail or tool. Parameters. So the parameters are presented here, and if you need particular some discussion, please ask. But I cannot tell any particular. How to say information.
Mhm.
So these are the parameters, and
Okay.
so.
Так, как я понимаю, вопросы все исчерпаны.
The questions are finished.
Спасибо за хороший доклад и подробные ответы.
Thank you for your nice report and detailed answers.
Okay.
Спасибо,
Thank
до
you.
свидания.
Thank you. Goodbye.
Ну, на этом наша пана. Я благодарю всех, кто принял участие, и докладчиков, и тех, кто задавал вопросы, и обязательно
Thanks.
тех, кто мне помогал с проведением этой сессии.
Thanks to everybody, to the reporters, to those who helped me here.
Все, до свидания, всем хорошего дня.
Goodbye. Have a nice day.